everybody, welcome to Logical, Plausible, Probable. I'm your host, John Maddox, and tonight we're going to be reviewing the one, the only, Dr. James Tour and his response to Wannabe Dave, that guy who said he didn't know what he was talking about in Abiochem, to which the good doctor responds, boy, I'm top 50. You didn't even finish those attempts at organic chem. What is up, everybody? Welcome to Logical, Plausible, Probable late night show. Gonna have a review of episode number 10 from the one and only Dr. James Tour's Abiogenesis series on lipids, which we'll get into in just a minute. Before we do, want to let everybody know, in case you don't know about this, and a lot of folks who come and listen on a regular basis don't know about this, but I recently launched what I'm calling the Conversation Starter Spring Collection. You know, I got to be I'm going to be a clothing designer. Got to have, some insightful names for the collections and such. So if you like some of the different jabs and want to be able to spark some conversation with different folks, many of who don't actually, the average person doesn't really think about a lot of these things, about their very existence. They just accept what they are told by the quote-unquote experts, many of which called out by Dr. Tour in this series, of like, hey guys, you don't actually know what you're talking about either, or you're glossing over the complexity in order to maximize your funding and repeat funding for your origin of life research. So if you want to help kind of kickstart some of those conversations, head on over to the Teespring site. Link for that is in the description. And if you use the code LPP30, get 30% off, because good grief, Teespring charges a lot of money for t-shirts, but they got all the logistics and the drop shipping sorted out. So head on over there, use code LPP30 for 30% off if you like any of those. I'm just showing some of the more popular ones. I got some different, there's more designs than that, but those are some of the most popular. And actually, the one on the bottom right, the God Established Infinity, is actually the most, right now, is the most popular of the designs so far. So anyway, we're going to get this review kicked off here in just a second. Due to the porn bombing, anybody who wants to join, please tag me in the chat. Let me know you want to join. And then I'll post the link real quick in the side chat for people to be able to hop in, join the stream, and then start having ongoing conversations. Let's get into this. I said I'm kind of doing a reverse review, starting with the hard stuff, and we'll go back to the easier stuff in what Dr. Tour was covering. But in this one, the lipids, which is one of the favorites from the Evo atheists, especially on YouTube. Oh man, we can have lipid bilayers. It's no problem whatsoever. It's totally accounted for. No big deal whatsoever. Yeah, that's not really the case. So, all right, without further ado, let's get into episode number 10, Lipids, from a course on abiogenesis by the one and only Dr. James Tour.
Lipids and the cell membrane. The reason for this lecture series on abiogenesis, if it's your first time joining in, this is for you. Dave Farina posted a video entitled Elucidating the Agenda of James Tour, a defense of abiogenesis. And I'm James Tour. You can see the description box to his video. I hope you go and watch that so you can see what he said. After watching that video, I was confused about almost every slide and every statement that Dave Farina presented. There were numerous gross scientific inaccuracies in his claims, in my opinion. Every slide of his was wrong. Since others might be likewise confused, I will use the Farina video with timestamps as a launch point for this series of lectures. I'm thankful for Dave. He has his YouTube site, Professor Dave Explains, so this is a shout out for his site. I haven't looked at any of his other videos, only this one, and the only reason, it's not like I happened upon this. There were many people that wrote to me that said, you got to see this. You got to see what this guy Dave has said about you and about about the chemistry that you speak about. So it wasn't just about me. It wasn't just about the chemistry. It was a lot about me as well, but I'm not commenting on that. I've got all sorts of problems that Dave doesn't even know about. Dave psychoanalyzed me a lot in that video, and he picked out problems that I have that I didn't even know I had. I know I have a lot of other problems, and so that's not what I'm talking about. It's commendable that he's trying to teach the masses. I don't want any contest with Dave Farina. If you're thinking about a contest and who's winning, I'll just proclaim Dave the winner. How's that? So this is not a contest. I'm just trying to bring clarity because I think that everything that he taught in that video was wrong. Other synthetic chemists, I hope you critique me. Point things out. Give me a critique. I want to know that. If I've said things wrong, point that out. If I've said things that are good, you can point those out. Let me know what you're thinking. Do you agree with me on this? Where are we on it? Lipids and phospholipids. A lipid is a compound that shows significant solubility in apolar solvents. That means things not like water. So things more like hexane or gasoline, that would be an apolar solvent. Liquids are defined by behavior rather than by precise structure. They typically contain a polar functional group, but have significant hydrocarbon content. So they have a polar head group, something that's soluble in water, and they're hooked to a tail that generally by itself would never be soluble in water. Phospholipids are lipids that contain a phosphate group. Membrane phospholipids are built on a glycerol scaffold. This is glycerol, this compound right here. It could be called glycerin or glycerol or 1,2,3-trihydroxypropane. Two of the hydroxyl groups of glycerol form esters to fatty acids. Glycerol is achiral, but it bears enantiotopic hydroxymethyl groups. So this is achiral, it's not chiral, but these are enantiotopic hydroxymethyl groups, meaning that if you functionalize one of these, immediately that then becomes a stereogenic center. And so then it would become a chiral molecule. When the two fatty acids are attached, the glycerol component bears a stereogenic center and the molecule is chiral. So as soon as you attach one to one of these hydroxymethyls, you get a chiral compound. And then usually you have both of these, and then this one attaches usually to a phosphate and then an ethanolamine molecule, but we'll see that. The remaining hydroxyl group of the glycerol backbone is often connected to phosphoric acid as a phosphate ester. So you get this phosphate ester forming. So this is your typical lipid with this phosphate group on one end. The phosphate is then connected to a protonated ethanolamine molecule in another phosphate ester linkage. So this is ethanolamine. It'll come in, and now you have a homochiral system and its stereogenic center. And we're keeping in mind, we're just thinking about these simple phospholipids with one stereogenic center. Sphingolipids have 4 possible stereoisomers, and only one exists in nature, the 2s3r. But we'll just keep it simple here. And so this is a typical lipid where you have something like this. Structure of phospholipids: polar head group and a hydrophilic group that interacts favorably with water. A nonpolar tail, a hydrophobic group that is not well solvated by water. So it's got a polar end, nonpolar tail. So the structure of a phospholipid, you'll have these two tails hanging down, and then this phospholipid with all its charged and oxygen groups as your polar head group. This is what interacts with the water. This goes down in the lipid bilayer. This is often represented as a sphere with these groups coming out. This is the stick model. This is the space filling model. When membrane phospholipids are added to water, and particularly when they are subjected to shear forces, they undergo a self-assembly to spontaneously form a phospholipid bilayer. If there are no shear forces, the yields are much lower. So really, if you really want to make good vesicles, you got to put these through shear forces or sonication. A monoacyl lipid destabilizes bilayer formation. So this idea that you can have a lot of monoacyl systems in there, it'll destabilize it. They undergo self-assembly spontaneously such that you have polar groups on one side, the non-polar groups pointing in, and then another side with another layer of these phospholipids where the polar groups are down here, the non-polar ends are sticking in, and so you have from the top and bottom the non-polar groups interacting, and then the polar groups outside. One of these is going to be outside to the biological world of an aqueous system. The inside is going to be to the inside of a cell. All right? Cell membrane transport properties. The phospholipid is generally impermeable.
Quick pause. I'm getting some entertainment from the side chat on this whole Dr. Behe, Dr. Danny Boy, and ultimately SFT getting himself blocked from Creation Myths, also known as Dr. Dan Stern Cardinal. Yeah, that was a very interesting interaction between Behe and Cardinal tonight, or earlier today. Danny Boy would not shut up. I mean, he just ran his mouth with his talking points over and over and over again. He just didn't shut up. And I mean, I would wager if you timed that out, it was probably a 70-30, maybe 65-35 split between the host talking and the guest being able to actually respond. I mean, because there was pretty long expositions from from Dan. But I mean, overall, I thought it was an interesting interaction. I think I would like to have seen Dr. Behe be a little bit more. Well, I guess he did kind of counter some of Dan's rather overconfident talking points. But yeah, that was an interesting. That was definitely an interesting deal for sure. I'm not sure. I haven't decided exactly how I feel about that one yet. But in line with what we're talking watching here with Dr. Tour, as you really start to contemplate the overarching macro level requirements for abiogenesis, well, just any biological system. Abiogenesis obviously has to account for these, but when you think about the most quote unquote simple forms of life that have all of these different components that are necessary for their existence, and then Dr. Behe kind of made this point as well earlier today to Danny Boy of, so you're relying on there being a slight modification to a one binding site. Like you're ignoring all of the other requirements for that component to even exist, and all of the underlying necessities from on both on a chemistry level, on a information level, on a functionality level. Like there's all these different things you have to account for, and you're over here being like, well, there's a little nick over here that we're being able to use to put in a screw. I mean, to me, it really blows the mind, the level of myopic hyper focus these people come up with in things that are like so minuscule, and then being like, hey man, if we get a bunch of these minuscule things over and over again, somehow we're going to have an entirely new deal. It's going to be awesome. And I'm guessing, and reinforced by today's conversation with them, and it'll be extenuated here with as we review Dr. Tour's lecture, they okay. In my interaction with Dan a couple weeks ago, I literally read from a 2019 paper that was doing a review of evolutionary algorithms and showed that they could optimize on a small plane of existing function. Then they plateaued and were unable to get new systems. This is an established premise. It is now being shown. There's multiple papers. I mean, there's paper after paper on this. Like, hey, this is the problem we're running into. And then we still have evolutionary biologists running around talking about like, oh, we had a slight mutation in a binding site, and ignoring like what has to bind there. Like, what do you need to have that have any relevance whatsoever? It's truly amazing. All right, enough of my tangent. Let's get back to Dr. Tour. Oh, and if anybody wants to join, tag me inside chat. I'll post the link to the stream. We can hop in so we can avoid the idiotic porn bombers.
Permeable to ions. Ions don't get through it. Some uncharged molecules like oxygen diffuse readily through the cell membrane. Substrates that are insoluble in hydrocarbons do not pass through the cell membrane. Substrates that are highly soluble in hydrocarbons get stuck in the phospholipid bilayer. Drugs must be carefully designed such that their solubility allows them to pass through the phospholipid bilayer and enter through the phospholipid layer and then enter into the cell. It takes a lot of design to do that. The cell membrane is a large phospholipid vesicle in which there is a phospholipid bilayer. Bacteria can have a double lipid bilayer, and most have a peptidoglycan layer constituting a cell wall rather than merely a lipid bilayer membrane. So actually bacteria, which we say, oh, we didn't make a eukaryotic cell first, it must have been a bacterium. If that's the case, the lipid bilayer is going to have to be a lot more complex because we have actually a cell wall where we have this peptidoglycan layer. But in any case, you have this cell membrane, and you have one side facing outward toward the water, another side facing inward, and there's these embedded proteins in it. These are essential for any cell function. And these embedded proteins have different jobs. And if you look down over the top, so here's the bilayer, there's this protein in there. If you look down over the top, you'll see that this particular protein allows potassium ions in and out. And it has a particular size that allows ions in and out. You have to be able to keep proton gradients. You have to be able to keep the charge in the cell different than the charge outside the system to keep a good proton gradient. And these integral proteins in this bilayer allow certain molecules to get in and certain molecules to get out. They're very selective. If you just have leaky cells, you're going to have dead cells very quickly. Researchers have identified thousands of different lipid structures in cell membranes. They move in swarms through periods of cell function. It has never been shown that a homogeneous lipid bilayer system can operate as a suitable cell membrane. Although all protocells are just homogeneous cell membranes, it's never been shown that something like that could operate as a cell. You have to have different types. That's all we know about in cells today. Lipid bilayers surround subcellular organelles such as nuclei, mitochondria. They all have their own lipid. So you have your outer vesicle, the lipid bilayer, and then inside you have another lipid bilayer around the nucleus, another lipid bilayer around mitochondria, and that's in the eukaryotic cells, which are themselves microsystem assemblies. Each of these has their own lipid composition, different from the host vesicle. So each of these has their own lipids that make it up lipid composition. Lipid bilayers have a non-symmetric distribution between the inner and outer surfaces. And this has never been shown. It has never been shown that a symmetric composition can operate as a cell membrane. So if this is outside of the cell, this is inside of the cell, you have a lipid bilayer. The constituents of the lipid on this side, on the outside, are different than these lipids on the inside. Every protocell experiment that I've read about, they're all the same. We have no idea if a cell can operate if you have a symmetric lipid bilayer. Protein-lipid complexes are required passive transport sites and active pumps for the passage of ions and molecules through the bilayer membranes, often with high specificity. Lipid bilayers have vast...
And something on that in line with the portals that he's referring to, that really, I know different people have talked about this in relation to the prokaryote to eukaryote evolution, where this takes on a whole new layer of significance. When you're getting into, not only are there portals, not only are there different keys that are activated and deactivated, you're also getting into things like dual authentication, passcode necessities. And to me, when you really reach the level of you have dual authentication to get through the doorway. Ladies and gentlemen, in the era in which we live of technology, how many of you, just think about this for un momento, how many of you have dual authentication set up on your login for one of your online accounts? Or let's say you log into your Gmail account from a new device. What oftentimes happens? Hey, we don't recognize you. Can we? We're going to send a code to your phone to input an access code, a secondary access code that you're unaware of. I mean, like, there's all sorts of things like this. You have all of these additional access points that require a pre-existence of knowledge in order to account for it. But in this context, what I'm talking about now, it's like, yes, the functionality has to exist in the code and has to be automated, and you have to know what the answer is, right? Well, in the same context, you can think about that in relation to what's happening in biological systems. We have dual authentication. How do, on the other side of the doorway, on the other side of the membrane, where is the pressure? How do you just randomly form a protein and another protein and then an intermediary protein that is necessary for protein A to be carrying, and when it interacts with protein B then recognizes, oh, you're the protein A and you have the key, I'll let you in. If you don't have the key, I don't let you in. I mean, this is so straightforward of a premise, in my opinion, when it's like, now that we know this exists beyond all doubt, we know this for a fact, it exists. How then is it remotely plausible to conclude that that does not require a foreknowledge intelligent agent to execute? Let's continue.
numbers of polycarbohydrate appendages known as glycans. These are essential for cell regulation. Nobody knows how these were made in a prebiotic system. And so to think that you can just take a bunch of salad dressing and get these sorts of assemblies is wrong. And anyway, your salad dressing, all of that came from biological sources. We're dealing with prebiotic earth here. So in that video that we're talking about the synthesis. It was written, most lipids are easy to synthesize. Okay. Well, then he shows us a triglyceride. So he's showing us groups coming off of this glycerol molecule. But it has now a stereogenic center because R1 and R3 are different. How did that stereogenic center arise in that homochiral molecule? If all of these are easy to synthesize, how did that happen? We have no idea. Some have said,
and lipids like triglycerides can be synthesized easily. Any biomolecule is easy to synthesize.
Well, the improper stereoisomer of the lipids are known not to function in cell operation. And so you can see that article. So you have to have the proper stereochemistry there, or else the cells don't function. You can't have this mixture. And we'll talk more about how important chirality is. In that same video, it says,
amphiphilic lipids spontaneously form ordered structures. As we mentioned earlier, this is how soap works. Bilayer formation is a spontaneous process due to the amphiphilic nature of phospholipids. Although in prebiotic absence of phospholipids, the first membranes can have been bilayers or even monolayers of fatty acids or other simple lipids that can easily have arisen spontaneously.
Could you please tell me how a fatty acid on early Earth could have formed, where you have methane molecules could have strung themselves together to get a fatty acid and with a carboxyl group at the end? You want to show me the aldol chemistry that's easy to affect so that you can get a fatty acid? I'd love to see that. Fatty acids today are isolated from natural sources. Just even a fatty acid hydrocarbon chain with a carboxyl group at the end. Try to do that on a prebiotic Earth. Some have proposed hydrothermal vents as a route to fatty acids. And there's this paper from McCullum and Seawald, and this was a review article entitled Abiotic Syntheses of Organic Compounds in Deep Sea Hydrothermal Environments. There have been suggestions that the Fischer-Tropsch type syntheses in hydrothermal vents can afford fatty acids, where carbon monoxide or generally one carbon oxygenated compounds can be reduced with hydrogen. The temperature in excess of 150 degrees and high pressures would be necessary. However, the article above states, quote, while hydrocarbons and other organic compounds have been observed in hydrothermal fluids and associated mineral deposits, criteria that can be used to differentiate the abiotic compounds from those derived from other sources have not yet emerged. Experimental studies have shown that light hydrocarbons and more complex compounds can be synthesized under certain hydrothermal conditions, while other experiments conducted under similar conditions have failed to produce organic compounds except for methane. It is not yet clear what factors control whether or not synthesis can proceed, making it difficult at this time to identify with certainty those environments within natural hydrothermal systems where abiotic synthesis might be occurring, unquote. In other words, thinking about just even where a fatty acid comes from before there's been biology around in a prebiotic system is hard. And even if you look at hydrothermal vents today, it's hard to know what is the source of the hydrocarbons that are coming out. Is that really due to a Fischer-Tropsch type reduction occurring? Or is that due to oil products that are under the ground that are of biological origin? It's hard to discern that. And isotopic ratios can help to discern that, but still it's hard. It is possible that fatty acids may have come from Fischer-Tropsch reactions. We can't rule that out. But again, it's not entirely clear, and they certainly don't spontaneously arise. There's a proposed glycoaldehyde route to fatty acids. So some ideas have come out on this. And this was an article from 1991 where this proposal was first given in the Journal of Molecular Evolution by Arthur Weber. While there was a glycoaldehyde route proposed to fatty acids, no such route has ever been demonstrated under prebiotically relevant conditions. So even making fatty acids is hard to think about being done under prebiotic conditions. It's not so easy. Can fatty
One of the things I find very interesting about all this, throughout all the these lectures, the interactions, the ongoing back and forth pontifications from both sides, to be fair, but when it comes down to one of my favorite statements of the difference between confidence and arrogance is being able to back up your BS. Well, it seems to continue to become clear that the Evo atheists, the OOL researchers, and the big talking propaganda artists here on YouTube, they like to talk with the utmost confidence. And yet, as Dr. Tours is pointing out, and continuing in this context of in relation to the lipids and the fatty acids and such, nobody is backing up their BS. Like, none of them are being able to back up their claims. It's very, at the end of their papers, it's, oh, well, this doesn't actually apply to a prebiotic environment, or, oh, well, we didn't actually do this, or we used relay synthesis, or, and just, insert countermeasure over and over and over again. And somehow we're the ones that are accused of being overconfident in our God of the Gaps worldview, when the ultimate irony is that those in which we are engaged are actually the ones who have basically no foundation, or at best a tentative quicksand foundation for their talking points, and then they can't actually back them up. It continues to be very ironic. Oh crap! Let's do that. That's where we were.
Some have proposed hydrothermal vents as a route to fatty acids. And there's this paper from McCullum and Seawald, and this was a review article entitled Abiotic Syntheses of Organic Compounds in Deep Sea Hydrothermal Environments. There have been suggestions that the Fischer-Tropsch type syntheses in hydrothermal vents can afford fatty acids, where carbon monoxide or generally one carbon oxygenated compounds can be reduced with hydrogen. The temperature in excess of 150 degrees and high pressures would be necessary. However, the article above states, quote, while hydrocarbons and other organic compounds have been observed in hydrothermal fluids and associated mineral deposits, criteria that can be used to differentiate the abiotic compounds from those derived from other sources have not yet emerged. Experimental studies have shown that light hydrocarbons and more complex compounds can be synthesized under certain hydrothermal conditions, while other experiments conducted under similar conditions have failed to produce organic compounds except for methane. It is not yet clear what factors control whether or not synthesis can proceed, making it difficult at this time to identify with certainty those environments within natural hydrothermal systems where abiotic synthesis might be occurring, unquote. In other words, thinking about just even where a fatty acid comes from before there's been biology around in a prebiotic system is hard. And even if you look at hydrothermal vents today, it's hard to know what is the source of the hydrocarbons that are coming out. Is that really due to a Fischer-Tropsch type reduction occurring? Or is that due to oil products that are under the ground that are of biological origin? It's hard to discern that. And isotopic ratios can help to discern that, but still, it's hard. It is possible that fatty acids may have come from Fischer-Tropsch reactions. We can't rule that out. But again, it's not entirely clear, and they certainly don't spontaneously arise. There's a proposed glycoaldehyde route to fatty acids. So some ideas have come out on this. And this was an article from 1991 where this proposal was first given in the Journal of Molecular Evolution by Arthur Weber. While there was a glycoaldehyde route proposed to fatty acids, no such route has ever been demonstrated under prebiotically relevant conditions. So even making fatty acids is hard to think about being done under prebiotic conditions. It's not so easy. Can fatty acids really serve as cellular membranes, as some claim? The first membranes can have been bilayers or even monolayers. Do you know any example? Show me any example of a monolayer acting as a cell membrane. This is grabbing things out of the air and proclaiming it from the rooftop. I just thought of something. I think I'll proclaim that with a high degree of confidence. Let's see what the literature says. Here's an article that came out in November 2020 in Nature Chemistry, the top chemistry journal, Nature Chemistry. And here's what Neil Devaraj writes. Quote, all living organisms harness proton gradients across phospholipid membranes to generate energy. Vesicles formed from simpler amphiphiles, such as fatty acids, are unable to maintain proton gradients, suggesting that diacyl phospholipid membranes appear early in the origin of life. Okay, so this Origin of Life researcher tells us that fatty acids alone cannot, lipids made from fatty acid membranes cannot maintain proton gradients. So all of this nonsense that you can make this from salad dressing is utter nonsense. Cells don't work that way. We are told in the literature that fatty acids can't maintain a proton gradient. Without a proton gradient, you don't have life. So phospholipids must have been around from the beginning. That's what that says. So you've got to stop grabbing ideas out of wherever you grab them and apply them here. It can't happen. You can't just proclaim these things. Whoever does that. One cannot suggest the spontaneous synthesis of fatty acids. And even if there were fatty acids, they would not suffice as cell membranes. Furthermore, this is not how soap works, as some have claimed. All right, so here's what Dave Rogers' article. So he has this whole article on enzyme-free synthesis of natural.
I love when Dr. Tor talks about the salad dressing, and it's not so easy to just form and everything, because it really is amazing. I mean, I believe in one of my debates with Erica, she made the argument from the standard atheist talking points that they were accounting for lipid bilayers and all these kind of things. But then, as Dr. Tor just pointed out and just read from, I think it was a 2020 paper, they weren't accounting for the, these things that they're playing around with don't actually account for the proton gradient. So you got to come up with some other explanation to account for this, but you don't have that explanation. But then you've got people running around on YouTube claiming that you do have the explanation for it. And I would also wager, oh wait, because I've heard the exact same talking points from people like quote unquote creation myths that issue very similar talking points, both to me and in other situations, and then claim that we're the ones that aren't keeping up with the latest and greatest research. It's extraordinarily fascinating.
Phospholipids. This is an article from November 2020. This is state of the art in the best chemistry journal. Let's see how he supposes that phospholipids could have been made in a prebiotically relevant synthesis. Well, what he does is he starts with this lysophospholipid, this lysophospholipid LPC right here. It already bears the stereogenic center, and it already bears the phosphate. Where did he get this? Did he make this prebiotically? No. He bought it from Avanti Polar Lipids Incorporated. And I know the owner of that company, Walt Shaw. And they get this from biological sites. And Avanti obtains the homochiral material from a biological source. They put it in a bottle and they sell it. There's no known prebiotic-like route to this homochiral or even racemic compound. Show me the route to even the racemic compound. You got to have a double bond there. How do you get a Z double bond there? The commercial thiacholine chloride was synthetically coupled with commercial oleic acid from a biological source. Just even oleic acid. This comes from a biological source. This doesn't wander around on a prebiotic earth, and it doesn't form spontaneously, I can tell you that. It was synthetically coupled with commercial oleic acid from a biological source using a commercial carbodiamide, that's a human-made coupling agent, in dichloromethane, a human-made solvent. There's no dichloromethane on an early earth. Nobody suggests that. Under argon, which is an inert gas, to make the thioester 2B. And you see that on the next page. So this he makes by a non-biologically relevant route, and this he buys. And then using an enzyme-free condition, he allows this hydroxyl to attack that carbonyl and to kick that thiol out, and that will then form the phospholipid of interest. He runs this at a pH of 10.6, which is quite high. So he's got it quite basic here. But okay, we'll give him that, and he runs this at 37 degrees, so that'd be a hot day outside. Let's look today at the syntheses of the origin of life, people. Are they prebiotically relevant? We've seen cases before where it was hard to think that they were prebiotically relevant. Let's look at the one today. Remember what I told you. This is what these guys do. This is their little secret. They do relay synthesis over and over again. They take A and they mix it with B, and they make a series of compounds. One of the ones in that series of compounds is the one they want. But they don't use that. They just make that some other synthetic way, or they buy it, and they go on to the next step. So they take this compound, they mix it with C, they get a series of different compounds here, but they don't use that. They take that, they either make it synthetically or they buy it. So the poor prebiotic earth would be stuck with this mixture. What am I going to do? And the origin of life researcher says, well, That's your problem, not mine, because I can buy it. And they leave the prebiotic earth stuck with that. They don't know what to do with it. They don't have no idea how the prebiotic earth dealt with it and brought that on to the next step with all these other competing things in there. But that's where they leave it, and they do this over and over again.
Man, origin of life research to prebiotic earth. That's your problem. I'm gonna buy it. It's too good. It really is amazing. The fact that they say this stuff with a straight face and like actually get published while their little minions run around like, so when are you guys gonna get a research paper published? It's like, so in the so let me get this straight. You're saying that if I don't have something published where they let people pull this kind of crap off, therefore my argument must be invalid. Yeah. Yep. Sorry. I'm not going to take you too seriously on that one. It's getting it's really getting irritating. Caleb's making some good points in the side chat too about the fact they in the textbooks it's life just must have spontaneously formed at some point in prebiotic earth. It just happened somehow. Let's just accept that it did. We exist, therefore that must be what happened. No way to account for it. As he says, it's willful ignorance. I agree completely.
Okay, so here is Dave Raj's prebiotic route. And again, I'm not picking on Dave Raj here. I have real respect for these folks. I really do. So Dave Raj purchased these starting materials for his prebiotically plausible route. He purchased oleic acid. He didn't make it. All right. Choline, this choline thiol chloride. He purchases this and he couples these under these conditions that he say could be prebiologically relevant. All right, to get this compound. But he already purchased this. He didn't make this by some prebiotic route. And he purchases this compound, and now he couples these two together. So let's see this. Reaction scheme for the dicyano-diamide mediated condensation. That's this compound, this mediated condensation of oleic acid and thiolcholine chloride. This is one of his main points in his paper here, to form the thioester 2B. So this is the reaction scheme. The comparison of extracted ion chromatography corresponding to M/Z 384. That's the mass spectrum positive ion mode for an analytical standard sample of 2B top and 2B generated in the reaction bottom. A turbid dispersion of oleic acid and dicyanamide was prepared. It was turbid because this compound, oleic acid, is not that soluble in water. Was prepared at 0.1 mLs of aqueous hydrochloric acid at pH approximately 1. So you got a pH of 1 here. Remember in the last slide, he had a pH of 10.5. Now he's got a pH of 1. It's easy to do that in a lab. You got to ship these things probably a long distance on a prebiotic earth to get this to happen. In one place it's acid, and one place it's strong base. Into this choline thiol chloride is added, and the dispersion was tumbled for the 37 presented. There were numerous gross scientific inaccuracies on a prebiotic earth. Well, it could have been made from this Mansi paper. He really didn't have it. The only thing he made it with, he didn't make it, and he takes 4-dimethylaminopyridine, which is a human-made reagent, and he mixes it with the 3-dimethylaminopropyl and ethyl carbodiamide hydrochloride. That's this EDC coupling.
And I really hate the way YouTube's got this. It's really obnoxious when you click the wrong spot and go back to the beginning every stupid time. In line with what Dr. Tour was just saying there in terms of having to transport stuff all over the place. I mean, it's kind of like, yeah, so ladies and gentlemen, there is a forest fire going down. Therefore, we know that forests can burn. But then you got a piece of wood in the ocean. Or it's in the lake. Are you going to have a forest fire in the lake? No, not unless you I guess unless the forest fire surrounding it evaporates the entire lake. I guess then you could have some wood that would burn where the lake used to be. But in the context of if there's a lake there currently and there's wood in the lake, it is not going to have there will be no forest fire in the lake. I mean, it's like, okay, so if you want this piece of wood that's in the lake to burn, you have to remove it from the lake and take it somewhere where it is not in water. Like, this is what we're talking about. at this point. And we're being told that no. There's some hypothetical scenario in which that piece of wood can burn in the lake. Yeah, I don't know how these people take themselves seriously when they're writing this stuff. It's just amazing to me. All right, now I got to figure out where in the heck I was. Oh crap, where was I? Okay, I know I was past this. Let's see here. Well, dang it. I guess we'll start right here.
And that's pre-biologically relevant to them. Prebiotically relevant. All reagents below were purchased for the synthetic process. This is how Dave Raj made the compound that he really used. He purchased oleic acid, purchases the choline chloride, and he takes 4-dimethylamino-pyridine, which is a human-made reagent, and he mixes it with the 3-dimethylamino-propyl and ethyl carbodiamide hydrochloride. That's this EDC coupling, this EDC compound. And he was added to a solution of oleic acid, which he bought, dichloromethane, which he bought, all human-made material. This is all human-made. This is isolated from natural sources. And thiolcholine chloride, which he buys at minus 78 degrees under argon. Because you're not really going to find that in a prebiotic environment. This is all human-made. And he separates it by column chromatography, and he gets it really pure, something that nature would never be able to do. No idea. But that's nature's problem, not his problem. Devaraj further suggests a prebiotic route to LPC1A. So he further suggests there is a prebiotic route to this. So here's how he made this compound 2B, and then he suggests a way to make the compound 1A. What he suggests is this. He writes this lysophospholipids, such as lysophosphofatidic acid, can be obtained by hydrolysis of cyclophosphate amphiphiles, which have been shown to be prebiotically synthesized from glycerol, fatty acid, and diaminophosphate in the presence of imidazole. All right, so what does all that mean? He says, okay, let me tell you how this thing could have been made in a prebiotic sense. How could this thing have been made on a prebiotic earth? Well, it could have been made from this lysophosphatidic acid. And so if you had a lysophosphatidic acid, this is very similar to this cyclic amphiphile. So this hydroxyl just comes in, attacks the phosphorus, out goes water. And I'll give him that. So somehow, if you could make this, then you could have made this. If you could have made this, you could have made this without any understanding of how he got that stereogenic center. So this is homochiral, what he bought from a natural source, from a company that sells it from a natural source. But he says it could have been made from this. And so he doesn't show us in his paper, but he refers us to another reference. So we look up reference 19 in the Devaraj paper. When we look it up, we're going to search for this molecule, because that's what he says you can make in a prebiotically relevant manner. So here's reference 19. It's a paper by Mansi. And in this Mansi paper, he really didn't have it. The only thing he made it with, he didn't make it with a C18 chain with a Z double bond. He made it with a C10 chain. He made it with a C9 chain. He made this with these chains, but not with this chain. This chain's very different now. This is going to be a whole lot less soluble. So it wasn't really made in this paper. Something like it was made that wouldn't have formed the same way. So you see, this is a C18 chain oleic acid derived. This is C10 chain, so it's very different in water, and it has no Z alkene, and it's not homochiral. There's no stereogenic center. This is racemic. If you're going to make this by any prebiotic route, this is racemic. This is not a stereogenic. This is a stereogenic center, but it's racemic. It's not homochiral. It's got both enantiomers here, but he used the homochiral one. How did he set that center in a homochiral sense on a prebiotic earth? Nobody knows, and Mansi doesn't tell us. But Mansi says, well, if you really want to see the synthesis of this, you've got to look up reference 18 in my paper. So Devaraj has us check reference 19 to the Mansi paper. Mansi says, well, if you really want to see that synthesis, you got to go to reference 18. All right, so we go to reference 18 in that paper. So here's reference 18 in the Mansi paper, and we go to this paper by Krishnamurti in Nature Chemistry, and then we go to look up that synthesis, and it's not quite there. He refers us to the supplementary material that is appended to this paper that you find online. Okay, it's 175 pages. 175 pages. Poor early Earth had a lot of chemistry to do. just to make this one compound. So he sends you back to this compound. It's not just this one compound. He's just
the level of investigation Dr. Tour is having to do here in order to figure out how they're claiming to have pulled this off, and then it's like, oh, all right, let's go down the proverbial rabbit hole. Where's the instructions? Oh, here it is. It's a 175-page instruction manual in order to create this, in terms of steps of the steps that are required to form this chain that's not even actually what you really would need to account for what you're claiming you have solved. Right. Okay. Ladies and gentlemen, you know what that is? In any other context, you would be considered full of bovine scatology. You are a charlatan. You are a snake oil salesman. If what you are claiming to have built isn't actually what you claimed to have built and sold as what you have built, and doesn't do what you said it would do, and when you told everybody it was going to do, and then you've claimed in your formal literature, to channel my inner James Downard, in the literature library that you're able to access these days, and it's like, well, hold the phone. So it's not what you said it was. It doesn't do what you said it did. You didn't make it how you said you could. And then you're telling me that what you built after is derived from what isn't even remotely close to what you claim it is. Yeah. So you don't actually have an answer. You're actually full of crap, and you're running around brainwashing people and simultaneously accepting millions of dollars in public and private funding to perpetuate the ongoing bovine scatology that you're spewing. Interesting. Again, as I've said in all of these, I really think that a lot of these origin of life researchers have got to be really, really irritated with the one and only wannabe Dave, because that guy who's sitting off on the beach and hanging out in LA is really causing them to get personally called out for the crap that they are being able to professionally benefit from.
Describes a lot of related compounds to this. So he takes this glycerol and he's able to make this cyclic compound, but there's no, this is now a stereogenic center, but it's racemic. He has not controlled the homochirality. And he can take these compounds with this DAP compound. He can mix this glycerol and this, he shows it with the C9 compound, not the C18 compound that we really wanted to be shown with. And he can get this cyclic phosphate. And where did the researchers get these compounds? They bought them. They didn't get them from a prebiotic earth type method. They bought them. Even though that Sutherland has showed a synthesis for this, nobody's going to use that synthesis. It's too messy. Prebiotic earth has to deal with it. That's prebiotic earth's problem, not these guys' problem. And what if they had to prepare them by a prebiotic-like route? How would they do that? I just wonder. How are you going to make a long-chain hydrocarbon by a prebiotic route? Remember, this is before biology. You can't get this from oil because oil is derived from biological compounds, presumably. Remember this route? We went through this before. Here was the route to that glycerol. So Sutherland has that route to glycerol, which he published formally. We've looked through this in a couple of different videos. Here's what he prepared. Here's what he wanted to get. It's so messy. He puts it on a vacuum pump. He can pump some of these volatile compounds off. If you put it on a good vacuum pump, you pump propane diol off. You see, you don't get it all off, but you can get some of it off. But how do you get a vacuum pump on early Earth? How do you evacuate something? How do you remove the atmosphere from early Earth? Really hard. How do you get a Rayonet reactor, a UV box? How do you get sealed tubes? How do you do degassing and add these different things? It's crazy hard synthesis. That's not prebiotically relevant, in my opinion. And then what you get is this mess. But does he use it? No, he does this. We get the relay synthesis. This is their little secret going all over again. All right, so then he did it with the C9 chain. He did it with a C9 chain, not C18. And it's an antiotopic hydroxymethyls, but he makes this racemic. What happens when the hydrophobic chain is increased from 9 carbons to 18 carbons, like Dave Raj would want? Dave Raj never mentions. And then you look up the supplementary material and you look up the synthesis. None of this is easy. A one-pot reaction of nanonoic acid, glycerol, in the presence of DAP and imidazole. And you mix these two together, and you add imidazole and about 4 drops of D2O, which is water, but this way you can look at it in the NMR, into an Eppendorf tube, and the resulting mixture was ground with a glass rod into a paste. I'd love to see that paste with not a C9 chain, but a C18 chain, and see how much different that paste would be. The paste reaction was kept at room temperature and ground for 5 minutes every day. The progress of the reaction was monitored by dissolving a small portion of the reaction in 500 microliters of D2O, just the pH, and then he gets the spectrum of this. He doesn't tell you the yield. How convenient. They don't tell you the yield on these things. Remember, we've seen this before, this game that they play. They don't tell you the yield. Unless it's a really good yield. They don't generally tell you the yield. No yield was reported, but you go to look at the spectrum. So he says, go find figure S118 to S123, and that means supplemental page figure 118 or figure 123. So you find figure 121. That's the one we want. So this is the unclean reaction mixture that he got for the C9 compound. Nothing for the C18 mixture, which was ever reported in this paper as Devaraj would have needed. The C18 would be much less soluble in the aqueous paste. And even this C9 mixture is terribly unclean. How would a prebiotic earth purify this compound to use it? How would it purify it? Look at all this extra stuff. Here's what he wants to get. Here's an authentic sample. And here's what he got. All of these extra peaks are all the extra sludge that from the reagents that he added. All of these extra peaks are all these extra things that he got. All right? So all these extra peaks in here. They made a clean synthetic sample using modern methods, dichloromethane, dimethylaminopyridine, dicyclohexylcarbodiimide, and column chromatography. So this is now what they use. They use this. This is really what they make. It's all relay synthesis the whole way. They leave poor prebiotic earth stuck with a problem that they themselves can't solve. And then you need the preparation of this DAP. Where'd they get DAP? Well, they bought it or they made it. Well, they make it. So here's how you have to make it. You take phenylphosphorodiamidite. This compound you can't get from a prebiotic earth. You buy it. There's no way that they've shown to get these aerial rings on a prebiotic earth to be able to do this. And it was suspended in 4 molar sodium hydroxide. I mean, that's really basic, but okay, we'll give them that. And in ethanol. Ethanol is not a prebiotic solvent. Dichloromethane is not a prebiotic solvent. Vacuum for 2 days is not a prebiotic method. So this is not made by a prebiotic route. You'd have to make this by a prebiotic route for this to be relevant. So you look up the synthesis of this. This is in the Watanabe paper in 1986. And Watanabe cites a paper from the late 1950s, and it's not prebiotic by that route either. So this is just, find Waldo. I mean, just I'm going to wear you out by sending you to all these references, and then when you go there, it's not prebiotically relevant anyway. So this is the way synthesis.
You can tell that Dr. Tour is starting to get a little get frustrated and even irritated a little bit with just the borderline. Well, we'll just go with Charlotte snake oil salesman action that's being executed. And now I honestly wonder, as he's describing, the different things. Oh, well, that's not prebiotic, and then here's why, and that's not prebiotic, and here's why. I honestly wonder if a lot of the folks that we interact with, at least I interact with here on YouTube, actually understand what that means in relation to the chemistry and just origin of life research in general. I mean, it's like saying, so just because I used my electron microscope doesn't mean anything in terms of what I was able to discover about the structure of the atom. I mean, no. It has no bearing on whether or not I was able to do that. I mean, come on, man. This is what we're talking about here. Well, just because I was able to I don't know, drill something and or do milling and create a design on a piece of steel, just because I was using a laser printer. Oh man, that has zero bearing on what is necessary in order to create those lines in a piece of metal. Come on now. No. The fact that I was using a laser engraver has no bearing whatsoever. It's like, You can't even make this crap up, folks. It's really amazing.
This is normally done. You take A and B, you get a mixture of compounds, you separate out AB4, and you take that material that you made and you carry it on to the next step. You separate that out, carrying it on to the next step. To do this, high yields at each step are essential to address the mass transport difficulty. If you start with 1 kilogram and obtain 1 gram or 1 milligram, you can't work with that because you don't have enough to carry it on. But somehow prebiotic earth has to deal with that. Isolating the product almost after every step is essential. That's how you really do synthesis. You have to isolate that product. It must be freed of impurities that consume the reagents and result in intractable products. If you don't free it and get clean material to carry on to the next step, what you'll get is intractable materials as you go along. They consume your starting materials. The molecules needed for life require many steps in order to obtain them, many steps. And you'd have to do purification all along. That's the way synthesis has to be done. But by not disclosing any of that and by just buying the thing that they've just made, they don't have to deal with the problem that prebiotic earth would do to have higher yields, to have isolation of products and purification, and the many steps that they'd have to go to do this. In this picture, which we've seen before, this is this prebiotic nucleobases, nucleotides, DNA and RNA. This is their presumed prebiotic route where there's no stereochemical control. These reactions that they use that I say are prebiotically relevant, there's no control of absolute stereochemistry and no homochirality. There's little to no control of relative stereochemistry. Only once in a while will they get, I think like in one case, they got relative stereochemistry, but not absolute, so it's not homochiral. There's little accounting of yield. They only tell you if the yield is good. There's little accounting of purification. How do you purify this? There's no accounting for mass transport through the sequence. A prebiotic earth would have none of these luxuries. So is it really prebiotically relevant? I don't think so. Origin of life researchers subject a prebiotic earth to constraints of ultra-low yields, racemic mixtures, impure mixtures, and reagent unavailability that the origin of life researchers themselves are unable to solve because they keep purchasing the compound that they want to go on to the next step. They have low yields at most, so efficient mass transport would be impossible. Intractable mixtures are obtained with little or no success in isolating them. The molecules needed for life require many steps in order to obtain them, and they would be every slide of his was wrong. Since others might be likewise confused. The molecules needed for life require many.
Oh my. Just because I bought a new tire to fix my flat, that doesn't mean that the manufacturing capacity to build the tire had to be in existence, and the design for the tire had to be in existence, and the wheel to which the tire is being attached didn't have to be in existence. No. Nothing to see here, folks. Nothing to see here. Totally reasonable to conclude that this created itself. Totally reasonable. We don't know how to make rubber, but hey, it formed itself.
Steps in order to obtain them, many steps, and you'd have to do purification all along. That's the way synthesis has to be done. But by not disclosing any of that and by just buying the thing that they've just made, they don't have to deal with the problem that prebiotic earth would do to have higher yields, to have isolation of products and purification, and the many steps that they'd have to go to do this. In this picture, which we've seen before, this is this prebiotic nucleobases, nucleotides, DNA and RNA. This is their presumed prebiotic route where there's no stereochemical control. These reactions that they use that I say are prebiotically relevant, there's no control of absolute stereochemistry and no homochirality. There's little to no control of relative stereochemistry. Only once in a while will they get, I think like in one case, they got relative stereochemistry, but not absolute, so it's not homochiral. There's little accounting of yield. They only tell you if the yield is good. There's little accounting of purification. How do you purify this? There's no accounting for mass transport through the sequence. A prebiotic earth would have none of these luxuries. So is it really prebiotically relevant? I don't think so. Origin of life researchers subject a prebiotic earth to constraints of ultra-low yields, racemic mixtures, impure mixtures, and reagent unavailability that the origin of life researchers themselves are unable to solve because they keep purchasing the compound that they want to go on to the next step. They have low yields at most steps, so efficient mass transport would be impossible. Intractable mixtures are obtained with little or no success in isolating them. The molecules needed for life require many steps in order to obtain them, and they would be unattainable by these routes. They'd be unattainable by the routes that are put forward. To those that make inaccurate claims on prebiotic chemistry, They've said things like,
any biomolecule is easy to synthesize.
even the simplest building block, the lipids, are not simple to synthesize. They are not. And especially when you don't have access to the fatty acids. They're not.
And lipids like triglycerides can be synthesized easily.
Wrong, wrong, wrong. You take this from I don't know where and you proclaim it. Why would you do that?
In prebiotic absence of phospholipids, the first membranes can have been bilayers or even monolayers of fatty acids or other simple lipids that can easily have arisen spontaneously.
Nothing arises spontaneously. There's no selectors and there's no spontaneous arising. Nothing arises spontaneously. Chemistry is not like that. The first membranes can have been bilayers or even monolayers of fatty acids or other simple lipids. But Devaraj contests. In the best journal of chemistry, November 2020, he writes, fatty acids are unable to maintain proton gradients. So you're wrong on that. All right, now I'm not addressing that video anymore. I'm going to make an appeal to my colleagues, my synthetic chemistry colleagues who work in the area of origin of life. You have no control of
I love how Dr. Tour has, he occasionally addresses some of the things from Wannabe Dave, but for the most part is kind of brushing him aside of like, can I believe people are taking this clown show seriously? I mean, it's painful. It's painful to watch.
absolute stereochemistry, homochirality, little to no control of relative stereochemistry, little to no accounting of your yields, little to no accounting of purification, no accounting for mass transport through a sequence because you play this relay synthesis game. There is enormous human intervention in every phase of the experiment. Really good synthetic chemists work on this. There's enormous human intervention. Would never be available on an early Earth. You don't make mention of that. A prebiotic Earth would have none of these luxuries. The origin of life researchers, those superb synthetic chemists, are generally silent on these essential synthetic questions. Reading the articles by the origin of life researchers leaves enormous holes which render their work prebiotically irrelevant and misleading the non-synthetic chemist. It is because of the claims that are made in these papers without qualifying all of these problems that people like those who made that video, like Dave Farina, who made that video, he's terribly misled by this. And doesn't it bother you to hear the claims that he made? These silly little claims that we showed on the last slide of any biomolecule is easy. Where did he get that idea? From you. That's where he got that idea. And then what he does is he makes videos, and 1 million subscribers hear these videos, and school teachers go into their classrooms and teach it. And homeschoolers learn this. And even professors in the academy are confused by this thing because they too believe a lot of the things that he said. This is not isolated to 6th graders. Don't you feel bad that people think of any biomolecule as easy? Where would they get that? This is not for lipids only. It is for almost all origin of life researcher syntheses. Though this happened in I pulled this all together in the lipids chapter only because the lipids video, because this is the video where I finished the 4th class of the necessary life compounds. This is the problem with it all. So I appeal to my origin of life researcher colleagues. I appeal to you. You got to help me out here in saying, yeah, there's so many problems here that really when you get to a prebiotic Earth, we're clueless because it's not just people like Dave Farina that are misled on this thing. It's famous biologists, like even those at Harvard, that think we're really close to cracking this problem, where we're nowhere close, and you know it. You got to step forward and help me. Reichert, who stepped forward and published an article and said, you got to have no human intervention, and you got to have, you can't keep using these purified chemicals and claiming that you've got this synthesis worked out. It's folks like that are beginning to speak the truth, and I really appreciate that. That's going to help the field. Let's work together to get this message out to the world. We have no idea where it came up with, and then maybe, just maybe, some students would come forward, and they'll start thinking about other ways that we could approach this, other ways where we could deal with these mass transport problems, the homochirality problem, that they'd think way out of the box, not like we're thinking, and they might come up with some solution here, because it must have been formed somehow. So with that, I'm going to wrap up. We still have to talk about a few other topics. Chiral-induced spin selectivity. Is homochirality really necessary for life? And then constructing a cell, all the assembly problems. And then we'll have one global summary. And then hopefully we'll be done. So if you want to hear about where the next video is, you can subscribe right here. And we'll ping you when the next video comes out. It shouldn't take too long. And you'll see that next video. Thank you for joining me. Thanks for joining us. If you want to subscribe, just click right here.
That's that whole video just kind of cracks me up of just the directness with which the good doctor is calling people out and just being like, guys, do you actually take yourself seriously? What is your professional credibility if you're going to claim that this stuff is, or that you actually have a grasp on what is required? It's I mean, we don't. We got nothing. And it's only getting, I mean, the further we go down the proverbial rabbit hole, the worse it gets, the more complicated it is, the more our realization that we don't have a clue expands. And then yet we still have people trying to convince others that we do. Man, it's crazy. One Cow Stampede. I've got I have the Donna Blackman paper. I think I posted it. Where did I post that? Let me see if I can pull it up real quick. Of course. So I live down the street from a fire station, and if you can hear the siren in the background, I swear we've been having idiots this past week in my neighborhood because, like, they've been driving past my house. I don't know what's going on. It's not summertime yet. Things shouldn't be burning. And Tony, I'm not going to lose. I'm literally having a conversation tomorrow night with his people, and we're going to discuss that and get that all wrapped up. Okay, what was I doing? I was looking for the Donna Blackman paper. So, for those of you wondering what I'm talking about, or One Cow Stampede's asking for, Wannabe Dave went on this whole tangent, separate from these videos, about how they had actually come up with a solution for the homochirality problem. And what they actually discovered was, actually, when I downloaded the paper and read through it, it actually states that no, they haven't solved a problem for let's see. There we go. No, we have not actually found a solution for chirality in a prebiotic environment. They actually haven't solved the whole problem in general, but on top of that, we have not found an answer in that context. So I'll get a link here. I'll post that for you, One Cow. Here is the link to and I'm going to pull it up on my screen here for just a second. So, right here. Hang on, where was that? I'll have to figure out where it was again. In here, basically, it says there's some. Man, where is that? I swear it was right here. Give me a second here. Let's see if I can find this. Well, I've had a long day. I don't know where it's at. It's somewhere in that paper. they talk about they make this clear specification that what they did was not prebiotic, and beyond that, that it was a multi-step process in order to pull off chirality. So if you don't have the chirality, you're screwed, but you have a multi-step process necessary in order to create the chirality. Well, that's a problem, ladies and gentlemen. That is a problem. Okay, so I guess if no one wants to join, I am going to call it a night on this stream. I hope everybody enjoyed, and we'll stay tuned to the for the next one of these that comes up, and then we got some other things that will be being put forth in the next couple of weeks. I appreciate everybody's support and help and ideas and things that people help to facilitate behind the scenes. Bring some new and cool stuff to the channel and to the community and in general to the world as we all try to come together and provide the resources, the knowledge, the connection points, and the arguments for explaining different aspects of our existence to those who are desperate to avoid the obvious. Before we wrap up again, for those of you who joined us late, we got the Conversation Starter Spring Collection of the shirts and sweatshirts and whatnot. It's out. Link to get to that is in the description. And right, Teespring is charging ridiculous prices, so I've got a 30% off coupon for everybody that comes here from the channel. So if you go there, use the code LPP30 and get 30% off any of the merch that's over there. And appreciate that. And yeah, as I love to end all these shows with, I would say, as you consider all of the things that are necessary for your existence, as you contemplate the fundamentals of your very existence and what is necessary for them to come into fruition, make sure that the conclusions you reach are logical, plausible, and probable. Have a great night, guys.